Okay, good. So we are live. To start with, well, do you guys have any questions from last time? Anything that's, any comments, questions? Everything is good? All right. If everything is good, then we can go on. And before going on, I'm going to do a small review of what we do last time. And so the thing is that we will start with reviewing what we did last time, which was solving the problem of sequential decision making when you have a model, when you know everything, and when you have the computational capacity to use all the data of knowing everything. So that is what we did so far. So you know everything, and you have the machine, the power to use everything, which is kind of hard in real life. So we will do today, we are going to slowly move towards the first real breakthrough in reinforcement learning, towards Q-learning algorithms. And the first part of such an algorithm is, like we had before, it's a part about policy evaluation. So this is the only part that we will cover today. We'll not cover the whole model-free Q-learning approach, which is the first really working approach, right? So we'll cover the part about policy evaluation. To remind you, oh, this is the wrong computer. Where is it? To remind you, this is where we were. So we, as I said, we started to see a situation. So we model our universe or problem with an MDP, right? So we have states, we have actions. When we perform an action, there is a probability of going to the next state, right? This is, and when we go to the next state, we get some reward. So this is not deterministic. When I perform an action, what will happen is still probabilistic, right? The winds can still blow you somewhere else. So there is a probability of what happens after that. And then you get some reward. And if all this knowledge is available, if all the probability information, all the transition probabilities, the rewards are already known, we had this approach, the dynamical programming approach, which consisted of two steps. The first step is pick some policy, right? That's where you start. Then you evaluate the policy. You see how much returns do you get if you use that policy. Right? So you evaluate the QPy, which is not just the return of a state, but you apply this policy after taking an action from a state and see how much return you get. So that part of it is called the policy evaluation, right? So you start with the policy, you get some QPy by evaluating the policy. We used in the last section, when we know everything, we used the Bellman equation to do the evaluation. He showed that iteratively applying the Bellman equation evaluates policy. Okay. Now that you have evaluated the policy, you can act greedily. And try and see if you can improve your policy. So can you construct a policy which is better than the last one by acting greedily? So this is the improvement step. And you go in this loop till you cannot improve anymore. That is the basic idea. So today we are going to say, okay, we don't know anything about the world usually, right? Usually, our knowledge of what probabilities are for doing something is not a priori given to us. We can learn it maybe, You can learn it. And there are also approaches where you actually learn how the world behaves. So you collect all the transitional probabilities, you learn them from the data, and then you apply more or less similar procedures to understand the world. That's an aspect we'll see about that later. But you will assume that we don't know anything about this. That's pretty usual standard phenomena. And second thing is, even when you do know, it's computationally easy. Just these things are computationally cheaper to not assume much about the world you know. So how do you proceed? So what would you do if you knew nothing about the world, but you wanted to make decisions? What will you have to do? Just philosophically, forget about mathematics, forget about programming. Philosophically, you are here, you don't know what's outside there. What will you have to do? Sorry? Try something randomly, right? What was the other thing you said?
Observations.
Observations. You collect more knowledge. So try something and collect information. So both your phrases put together, right? Try one thing, see what you get. Try another thing, see what you get. This is called exploration or whatever. So what you do is usually there is in such decision-making process, you're trying to play, say, a game. The book that I have in the thing, I wanted to. So as I said, I will talk about the project purposes things today a little bit, and then I will put something online. So that book has an example on blackjack. How many people know what blackjack is? Not many. Everyone knows. So this is a game, right? So it's a there is you can think of this. So if everyone knows this, then I have to absolutely not worry about it. So if I want to be an intelligent agent who goes there and doesn't have an idea how to play blackjack, which I am actually, I know how people play it. I have never played it myself. Okay, so how do I make money? Right. So first you will have to trial and error and see what happens till you start saying, oh, if I use such a policy, then it gets me better reward. So the first approach we will use is the Monte Carlo approach, which is where we'll begin. And the reason for this is it's conceptually very simple. The reason for starting with this is conceptually very simple, one thing. Second thing is, it converges, if it works, it converges quite fast. So if you are ever in a situation where something like that can work, use it. It does converge fast. It looks like the most stupid idea to try. It has its drawbacks, but it does converge fast. Okay, so what does it entail? So you need one more concept, which is this Monte Carlo kind of approach works when you play a game or when you go through a decision process to a final terminal state. Right? So it's hard to evaluate something like that for half a progression. Okay, so there is a terminology for it. The word is called an episode. So episode is a sequence of actions and states and action. Then you get to another state and then take another action. Reach another state, take another action, till you have hit a terminal, a final state. Right? So a sequence like that is called an episode. So you need a whole episode from starting till something terminal, right? For applying these things. So a priori, you can always say, oh, is it always going to be there? Can I always get such a sequence? For many things you do, like if you're playing a game of chess, you will end the game of chess. For blackjack, you will finish it somewhere. For many problems, there is a terminal state. Okay? So for all these problems, this is applicable. And what you do is you sample an episode. You go out, as you said, go out and experience. So you sample an episode till you reach the terminal state. You play the game of blackjack till you reach the terminal state, which is you either win or you lose or it's a draw. And you collect the reward during this one episode. To collect the whole reward. So I start from a state, or say state and action, and I follow a whole episode to a terminal state. And I collect the whole reward, which is denoted here by GT. Right? So this is for one sample. And you just keep sampling many times. And what do people do when you have many numbers? You take the empirical average. And that is what you assign as your state value or state action value. Simple. Does this make sense? Will this work? Or why will this work? Even before going to the next slide. Is this a meaningful thing to try? Will this work? You guys sit too far apart. I don't see how I can ask you guys to talk to each other. These days, it's not very common to ask students to talk to each other, so ever since we have COVID. But you can ask each other why you think this might work. No? Well, it is rather straightforward. Why averages work. There is always one reason why averages works, and we'll see it in a minute. But so here I have tried to put a sort of contrast. So suppose my sort of ugly handling of a picture. So I wanted to make a grid with a river flow. So the blue part is a river, and non-blue part is a land. And you want to go from the starting position to the end position. So there is one terminal position. Starting position can be anywhere else. And you have absolutely no idea in one case of what is in between. How fast can you go? Whether there are crocodiles in the river, right? Whether the stream is flowing left or whether the stream is flowing right. You have no knowledge of that. Where the stream is fast and where the stream is slow, you have no knowledge of that. Right? So if you have no knowledge, you will have to go through some trial and error process. And actually, you don't even know where the final state is, really. You know what to find. It's like a treasure hunt. Right? You know what to find. Somebody said, this is a treasure hunt. There is something we want to find somewhere across the river, and you're trying to look at clues, get there. Once you have done one path, so this ugly looking path is an episode. It starts where you want to start and it ends where you want to end. Right? It can be horribly complicated. A sample will never be close to the ideal path. But if you put some sort of information like what I have put on the other side, like if I know the speed on the land is twice as much as the speed in water. Right? So in the land, when you move vertically or horizontally, you have covered 1 unit distance. Right? So if you've covered 1 unit distance, you tax yourself by -1. And when you go diagonally from one square to the next square, you have covered a square root 2 distance. You tax yourself according to that, right? And in water, say your speed, well, you're half as slow, so to speak. So you tax yourself more, something like that. But this is realistic, right? So you can model something like that, which is also not so bad. Often what people do is make some assumptions like what you have on the other side, without really knowing what the system is. You can make some assumptions about it and proceed. That's one way of proceeding. The other way of proceeding is just create sample episodes, which can be as horrible as the picture down there, and compute what reward you get, and create another sample thing and compute. So these samples have to be created how? They have to be created following a policy. You can have very weird policy, or your policy, as you said, can be random policy, where the random policies at every state, I toss a coin to see whether I go east, west, north, south, northeast, northwest, whatever. I can toss a few coins, and that decides which direction I go. So that could be a policy. That could be your first policy. And that's often a good policy when you don't know anything. A good policy is uniformly random, so a toss a coin policy. So first thing, create episodes and evaluate samples. So I will write down for once, and this will be probably very rare occasion that I write down a pseudocode. But I realized from some of the feedback, and I have a feeling about it, that many people who are from pure math background have no knowledge of writing these kind of things down, and people who do programming would look like, why are you writing this? So it's for benefit for some of you. For others who know it, it's fine. So this is the algorithm. This is what's called the first visit Monte Carlo algorithm. So maybe I will keep this. Oh, why is it sleeping? Wake up. So okay, I'm going to turn this off for a second. It's all, these things are all available also on. But I wanted to say what typically will happen is that you start from a state, you go to some other state by your policy, you follow it. So usually I won't say there is an action involved. Take an action, you get to state 2, take another action, get to state 3. And what can happen is you can loop back. You might loop back to where you started, right? And you keep going. So after you loop back, you maybe go on another direction. So action AN or SM. And some point of time you reach your terminal state. Okay. So in first visit Monte Carlo, what you're doing is you're only counting a state when you have first visited it. If you loop over it many times, you're not counting the subsequent visits. And the reason for it, I will just say, is that this is theoretically easier to handle. So as far as implementation concerns, as far as writing the code is concerned, encapsulating every visit is pretty much the same as encapsulating one visit. The code doesn't change by very much. But what you do is you start taking, you hit the terminal thing. Here you say, okay, of course, here my reward after this is 0. When I get here, my reward was what I get when I arrive here. So it's G equals reward at G, right? And so on. So I can always say the reward at anything here. So as T plus 1, and this is as T. So the reward GT is what I had before till here, plus, so I apply that, multiply that by gamma and R T plus 1. So if I got the reward till here, I can just calculate it. But I'm not going to store it for this state. I'm not going to store it in my list. So I have a list of rewards. This is the reward list of rewards. List of reward collected in an episode. Okay. When will I put this reward in this list? When I know that I have not previously visited if this thing is not previously been visited. So if the state has not been previously visited, you append it to this list. Right? You keep doing this process and you get some rewards. You will get rewards for some of the states in this episode. Well, you'll get reward for all the states in this episode up to repetition. Right? Only one reward. Okay, so this function looks very much like the value function. As you're creating it, it is value function, but we are not saying what is the difference here. The difference is that we are not applying any probability. So we usually would have weighted the rewards by probability. Now, rather than that, if you collect enough episodes, you will get the weight out of probability just because the chance of getting to some trajectory depends on the probabilities. Okay? So this is the basic idea. And at the end of the day, I think so. This is the step. If you have, I think somewhere it says that is it. I think here it says if you haven't visited, update your reward. Okay. So, or have I written it incorrectly? I don't see it. So somewhere there it should be as the computation, right? So this is the algorithm. This is the algorithm. But we are here. So today I'm going to talk mostly about the algorithms of policy evaluation. This is one algorithm of policy evaluation. This one is easy to explain why it works. Okay. We'll take first turns understanding the algorithms, and then we'll also take some time understanding the mathematics behind it. Good thing about this one is the mathematics is more or less obvious. Why do averages work? If I look at average of many things, why do I have a good idea of what the value of that thing is? Is there an explanation of that? Law of large numbers. That's all there is to this algorithm, right? There is absolutely no. This algorithm works only because of law of large numbers. Okay. So every time you visit the state, this first time at least, because you're not looping around anything, you can consider that these as independent random variables. Their averages should converge by law of large number to the actual value. Okay. So this is the first visit Monte Carlo algorithm. It is actually efficient, although it's so mundane. If you can apply it in a situation, it is not bad actually. So there's no reason to be contemptuous about it because it's mundane. The thing is, there are two caveats about it. Is that there is variance in this algorithm. And the variance depends on how many jumps you have made along the episode, along the episodes. This leads to, at every action, there is a probability of what state you will get, right? It's not automatic. It's not deterministic. The action to state mapping is not deterministic in any. So underline, there is a hidden Markov decision process. There is a hidden MDP. The problem is nobody has given it to us. So there is a hidden MDP. This is the frame of mind we should have. A frame of mind is there is a hidden MDP. We don't know what it is. So when I take an action, there is some probability of getting into a new state. I am not given these probabilities. Right? But when I follow an episode, I will incur some variance just because there are these hidden probabilities. So this the disadvantage is that there is some variance in this algorithm, which sometimes is a critical thing to consider. If you have a process where you heuristically think will add up to a lot of variance, you probably shouldn't think of this kind of algorithm. Okay, but on the other hand, the good thing is it has no bias. You're actually really approximating the function you're trying to calculate. You're not trying to approximate it by some biased creature, like we will do in the next algorithm. So this algorithm is trying to approximate the real thing without any bias. The value this algorithm is trying to, so V of S is trying to become, is at any time trying to pretend that it is V by S. Right? So there is no bias in this. Okay. Any questions so far? All right. So there are some standard variants that I will like to talk about. The first variant is, of course, I've already said that, but I have written it out for I don't know. Well, if anybody wants to, if anybody who's listening to this streaming wants to say, they shouldn't say anything in chat. They should just maybe turn off the microphone and shout. Okay, because I think something moved here, but I don't know what. Anyways, got distracted. That's life, right? So this is stochasticity of life. I wanted to do something, tell you about this algorithm, but all of a sudden something flickers on that screen and I get distracted. This was not planned. Actions don't, real life is also very stochastic, right? But that's more philosophical. The first algorithm we have already discussed. So now you count every visit to a state and you average all the returns. Every time you visit, you also include the returns starting at that point, and you average all of them. Okay. This also actually requires law of large numbers to say this converges. But this time you have to be more careful. These things are slightly, the variance changes or something like that. So it's a little bit more technical, but it's not that interesting to worry about. Okay. So, but this algorithm is what is, as far as coding is concerned, there is not much difference between the two algorithms. Okay. So the last example, the incremental version, this is interesting, and it depends on whether you guys know about keeping track of what you call running averages or streaming averages in modern internet world. So this is just a programming aspect. It is not a mathematical aspect at all. Okay, so it says you implement the way you calculate the update. The jargon is update when you want to change a variable after encountering new information. You update that variable is by actually doing this kind of a change. So why does this work? Is this obvious to everybody? Has everybody seen such update? The running average update. So maybe I'll explain this in a minute, but this is more about how to implement. There is no new mathematics happening. But once you understand this, you will see this is the phenomena. This is the what do you say? This is the hidden trick. This is a hidden formulation in all the updates. So So suppose I am streaming something. Somebody is streaming numbers to me, and I want to keep the average of these numbers. Right? So I have a computer and somebody's sending me number x1 at time 1, and x2 at time 2, and x3 at time 3, and you get the picture. And I want to know at any time, I'm only interested in knowing, so let's just call it xt. At any time, I'm only interested in knowing what the average is so far. I'm not interested in knowing the numbers, but just the average at the current moment. Right? So this is equal to x1 plus x2 plus x3 divided by 2. So let me write this as numbers. Numbers are easier. Right. You all like writing numbers better. This is the only thing that I'm interested in keeping track of. Okay? But can I keep track of only this number without keeping track of any of these numbers? Without storing these numbers in any memory? That is the only thing. That is the only reason why you have such an algorithm. Can I keep track of the number un without actually keeping all of these previous numbers in the memory? Huh? There is a way, right? That's why I'm asking. So it has many names and I don't know them. But you see that everywhere, whoever comes up with this algorithm has a different name for this trivial piece of class grade 7 mathematics. So you can write this as 1 over n of xn plus the rest of them. So x1 plus x2 plus xn minus 1. Right? But this bit, I can write this as n minus 1 times un minus 1. Right? Because un minus 1 is the average there. So what can I do? I can write this as 1 over n xn plus n times un minus un. And minus 1, I've just multiplied it through. Is that such a hard piece of mathematics? So that gives me, oh, sorry. That gives me un minus 1 plus 1 over n xn minus. So this is equal to un. So if I look at this new formula of un, all I have to keep track of un minus 1. And as soon as I get the new xn, I can update un. I don't need to keep any of these numbers in my memory. Okay. So this is the formula that you will see all through this lecture. This way of updating. So what if you don't know the n? In some cases, sort of you don't know the n, is what will happen as you will see, and you sort of guess what n is. It's usually put in alpha or alpha t or something like that. So you guess an n here, and this is where much of this work goes on. So if you cannot, you can make some approximations.
Can't you just keep the calculus
Yeah, but this is actually more philosophical point of the end, that you are doing various kinds of estimates in various parts, and you don't know which is the right n to use. Sometimes, whenever you see the Monte Carlo kind of thing, you will see that the n is clear what n should be, so you write the n. So in this estimate that I have written for the Monte Carlo version, wake up. So in this case, you actually can keep track of the n, how many times the state has been visited. Every time you visit the state, you increment that. And when you update the value with the rewards, you use exactly the n that you need in this problem. Okay, so in this case, you can keep track of n, you should keep track of n. Sometimes your best way of thinking, oh, which update is this for this state? I have no idea because things have become jumbled up. All right. So then you have some sort of a predictor update. So you take your current mean and you update it towards this error. So the one way of looking at this formula is your new value is your old value, and it's updated towards this error. This is the error. You had been expecting this number. What had you been expecting? You had been expecting this number. What you get is this number. So this is your error. Okay? So you try to move your average towards this error, by at least a small bit. So this is the basic idea. You'll see all these algorithms following some logic like that. So we'll see how all of them. So first, I'm going to today, and maybe even in the next class, spend most of my time describing the algorithm, because it's good to know what they are. So, and then I will describe the mathematics, some of the mathematics behind it. And both has its advantages. But if you don't know the algorithm, there is just no point knowing the mathematics, is my personal opinion. And if you know the algorithm, you can have two motivations for knowing an algorithm. One motivation is just implement it, right? In which case you should not be interested in mathematics. But another motivation is, well, sometimes this algorithm doesn't work. Is there another problem where I can use similar algorithm? Or can I improve this algorithm? In which case you should know why at all something like that tends to work. That's why you should know the mathematics. So there are two separate things. Implementation is one motivation, and understanding and developing new algorithms or developing new solutions is another motivation. They're two different things. But we'll first look at the algorithms, right? Just have them for ourselves. In the worst case, we are at least able to implement them. All right, so where are we now? I don't know where are we now. Okay, so now we will be in a situation where we'll update not with now we'll update by some alpha here. And it might change with time. So we are not there yet, but currently we will update things using an alpha instead of an n, because we don't know what n should be really speaking. But if you can find a version of these algorithms, and maybe there are versions that you can keep track of n, then you can keep track of n. That's fine. Okay. So what does this do? So the problem with the Monte Carlo algorithm is you need a complete episode to update your knowledge of the policy. So I have a policy. I don't know how good or bad this policy is. I have to go through the whole episode, get to some end before I can update my policy. Right? I mean, imagine you want to update your life. You live your life with some philosophy, and you cannot go to the end and then update your philosophy, right? That's a little, yeah, whatever, you know what I mean. So instead, you just update every step. So this is the temporal difference thing, and maybe I want to make a to give a correct difference between them. So what we are doing in the Monte Carlo, oh, it's gone. Is it gone? What is the other one? Okay, maybe I'll write here. So in Monte Carlo, we took our sort of current evaluation of the say value function. It could be the same thing will apply to Q as A as well, yeah? But it's easier to always write V as first and then consider Q as later. So what we are doing is we are saying the value function, it doesn't depend on one reward, right? It depends on all the subsequent rewards. It depends on all the subsequent rewards. So we'll take all the subsequent rewards and get one instance of the value function, and then update this using one instant of the true value function. And so you update by one instance of this whole thing. So in this case, there is no bias in how we are updating. So this is the Monte Carlo. This is what we saw before. So this requires a complete episode. Requires an episode. And no bias. Okay, so now what we will call TD or temporal difference methods is you say VS, or forget about it. We'll do what calculus students learn to do. We'll just chop it off at the first step. Right? So now we are going to say this is the reward at t plus 1 plus gamma, the current value of S t plus 1. So we will update this using this information. What will we update this? We'll update this using this information, which is sort of chopping it off from going ahead. So this implicitly does, because now we have just added this guy. We haven't done the whole thing. Whatever was wrong here will remain wrong here. Right? So this creates a bias. This gives you a bias. Right? But on the other hand, since you're not jumping through so many steps where each of them is probabilistically determined from your sample, doing this step only one time has no variance. Okay. So this is the essentially the thing. Now what you do is, this is what you had now currently given the next experience or the next experience, you have come to this to be your value function. This is what you're thinking is the value function. Right? Now for the next bit, now you start thinking this is the value function. Whereas previously you thought this was the value function. So your error of what you observed, so this is your observation, and this is your assumption. So the error is, well, I think the way people write it is this way, so I was observation minus assumption. Okay, so this is always going to be your error. In most of these cases, if you have this philosophy in mind, you will see that you'll work out the right formula. In almost every example, if you have this kind of thing in mind, you work out the right formula. So this gives you RT plus 1 plus gamma, the current value of ST plus 1 minus the current value of the state. This is the error. And when you update, what do? Whenever you update a fraction of your error. So move the real value a fraction more towards the error. This is how most of these algorithms are designed. They're designed to move a fraction towards the error. So let me make this visible again. Oh, yeah. So every time you just make one observation, you don't have to go down all the way to the terminal state. Just make one observation. Every time you see, oh, if my Bellman equation was true, if the Bellman equation was true, I should have gotten the value to be the reward plus gamma times the next value. But of course, that would only be true for the true value function, not for our arbitrarily chosen value function. Right? So now we see there is an error in our observation to our assumption. So we change our assumptions a little bit. We update our assumption a little bit towards the observation. Okay, so this is also a fairly reasonable attitude, I would say. Right? Okay, so before I move on to making this complicated, so these are two simplest algorithms. Okay, and we will make things complicated now. Right, so any questions so far? Okay, good. Oh, that is it. Okay, so what does calculus teach us? I suppose even the ones of you who are doing data science, they know Taylor series, right? So you can approximate a function by first derivative. You can approximate a function by n derivatives. So the question is, if I can make n consecutive observations, is it better to approximate? Is it better to approximate my value using the n consecutive approximation, or is it better to just make one approximation? What do you say?
I mean, what do you mean by better? It takes less memory to do one.
It takes less memory to do one. That's a good point. Same memory is not my concern. Yeah, but there is still a little bit of an issue here, because in decision making, some decisions are important, and some decisions are less important. You know, but they have consequences, of course. What I start studying, or where I start working, or who I start living with, these are big decisions. So what I had for dinner yesterday can have me a little bit of trouble, maybe because I'm too hungry, my stomach is good or bad or whatever, can make me strong, but it's not going to immediately have big effect. Some decisions should have higher weight, and some decisions should have less weight. And the whole question is, which decisions are getting you towards more returns? That is what we are up to finding, right? We're not up to finding. So forget about it. In a policy, which decisions are actually the crucial ones is somehow, or which are impacting the most, are what you should worry about. And there is, of course, one direct approach. Once you can say, okay, let's just look at n-step approximation. So what I said is, if you have n observations, then you can write a slightly different way. So rather than just taking one reward, I think it's somewhere here. Take sequence of n rewards and then the value at the nth state. Right? Afterwards, the nth state beyond is what you get. As so this is now your new guess. So although this is not the terminology officially used, but you should always think of this g function as the guess, current guess of your true value function. So this is your current guess of your true value function. And of course, you update your value function to the error, what your current guess is and what you assumed, your observation, your assumption, you update it like that. This is just the same idea as before. Okay, so this is the n step, but it's actually not clear whether n step is better or which n is better, whether 2 steps is better or 10 steps is better. It depends on policy, it depends on problems, it depends on various things. Okay, so there being enough mathematics around, what will you do? You could try to take for every n, you could do something. You could just weight the n step of approximations. Suppose you have that freedom. So this is where we are going next. But this is, I want to motivate it a little bit more somehow. So by the way, even for this n-step versions, so no, this is the wrong one. So even for this n-step versions, the same thing holds. So now you have and more things in between. So you take first return, then the second return multiplied by gamma. There's the third return multiplied by gamma squared, and up to n. Right? So this is your n-step return. The same thing again holds. There is a bias. It's a little less bias than before, maybe. So this has actually, what has it done doing this n-step? It has reduced the bias, but what has it done instead? It has increased the variance. And this is the whole point. So when I say something is better, if your aim somehow should be implicitly to reduce bias, you're doing good. But at the same time, if your goal is to reduce variance, you're doing bad. So now this is with n, bias increases. Bias gets better. Variance gets worse. Right? And it's a trade-off. You don't know how much should you think about bias and how much should you think about the variance. So there is almost a standard trick whenever this happens. Whenever you have phenomena that are increasing bias, say decreasing bias, increasing variance, you try to take a weighted sum of these things and see if this stabilizes somewhere. So this is kind of a standard technique, which is what I will come to some point of time when we do the mathematics part of it. But now I'm trying to motivate you guys into understanding this. There is a mathematical reason to take a weighted average of this and find out if there is a good point where the bias is also good and the variance is also good. because one of them is increasing bias and one of them is increasing variance. All right. Okay. I remember. So what does it mean to increase bias? Just to be very clear, what does it mean to increase bias or decrease bias? It means that your random variable actually has the mean, which is the value you're looking for. As close to the mean it is, the less the bias is, right? So if my random variable looks like this, and what I'm expecting is the number here, and it's sort of moved here, the mean of this curve is here, then this is my bias essentially, right? And the variance is how fat or thin this thing is. Okay, so this is a conceptual picture to keep in mind. So this is the true value set. This is mu for your random variable, x mu, and this thing is your sigma, right? So having more variance means this becomes flatter. It has more uncertainty, which is bad. But having big bias means you're away from this value, which is also bad. Okay, so having big bias but low variance will look like your true value is here, and you have a random variable that looks like that. Okay, it has a big bias and very low variance. Is that any better? Not really, right? So one thing creates uncertainty and one thing creates the, just to keep the terminology clear. I mean, I from the responses, I reckon, so I got 24 responses, out of which barely 10 or 12 people said you're happy with stochastics. So I don't want to put, at this point, we'll do a little bit more of the theory properly. Okay? So we know what we're talking about. But this is what this means. Is this good for now? All right, so I have to see. Should be this one. All right. So this is the picture you will see in every presentation, every book. So I kind of also put it here. Obligation, I suppose. If everybody does it, you have to do it. So when you're looking at the TD, one-step TD, TD1, say, the first one that we took one action, got to one state, one new state, and you calculated the reward, and that is what you used as a biased estimate to update your current assumption on the value of your state. Right? And in the end step one, you do 2. If you go all the way to infinity, what will you get? The Monte Carlo, right? Because then you are actually updating to what the value along a certain episode is. If you go all the way to a terminal state, what you have updated is what Monte Carlo tells you to update. So this end step thing is an interpolation, so to speak, between the very biased temporal difference approach to the high variance Monte Carlo approach. So it's an interpolation. So why not take an average? Whenever you have this dichotomy between having to choose between low bias and low variance, you take a weighted average. So the weights here, I think they're written somewhere here. They're written here, I think. The weights here, they add up to 1. Obviously, right? So that is the whole point. So you're adding weights and you just take a weighted average. And now you guess. So now this is a theoretical, or again, either a theoretical algorithm or an algorithm that requires processes that have a terminal process. So you can only do this when you can get to complete episodes. So actually there is a term in literature which I don't want to overload terminology for everyone. If you update things when you have a whole episode, when you go all the way down to an episode and then you do your update, there's something what one calls sort of offline. So you're trying to learn when the whole event has happened. Whereas all the other processes were online, when you're just trying to learn in one step. Okay? So that is a terminology, but we'll maybe come to it later. I don't know how crucial I think it is. For mathematics, not so crucial, but we have to also learn real world stuff. So here, now you make the new guess as a combination of all your old guesses multiplied by some weight, and you try to update your value depending on this lambda parameter by this guess. So lambda is a parameter between 0 and 1. If I put lambda equal to 0, what will happen? You only get the first one, right? And that is basically the TD method. And when lambda is 1, you will kind of see that it approximates the Monte Carlo. Okay. So, so this is again something that requires you to know to work your way all the way through an episode. If you want to implement this like that, you need to know all the way through and work through an episode. So what can one find a way of doing things without working all the way through an episode? So this is the question, and there is actually a trick, but this trick is not. Well, there is a version of this trick. The version I am presenting right now, this is not exactly the same as the version here is not exactly the same as what we just discussed, the averaging version. Okay, the averaging version is a mathematical trick, and we'll come to it again. It is sort of an effort in finding. So you want to find a lambda. You want to find a lambda, which will be a number between 0 and 1, so that you have as little bias and as little variance in your resulting. So when you start plotting these things, when you do actually do implementation, you can plot out and see what the bias and variance can be. And you want to find lambdas which are most stable. So that is where the first bit, what we had in the last slide, is a theoretical tool. But of course, if you have episodic ability to work all the way till the end for your problem, then they still work in practice. You can still implement them. Right? But when you cannot implement them, there is a cheating approach. And which is what I will try to maybe explain here. So I will. Somehow this nice weather that we have, which is between -1 in the morning to 20 in the afternoon, is not good for people who have to give lectures because your voice becomes a little sore after a bit of. Well, I'm not complaining. By no means. Just I suppose you guys hear it, that I'm not sounding very well. I'm probably not even 1 hour in the lecture. So. Okay, so what are we doing now? So if you look at a particular state, right, and what is important? So you follow a policy, start somewhere, and you go around. So this is my state. So basically, whenever in time, so these are all my states. So say S1, S2, S3, whatever. And when I follow the policy, I go from one state, and this is the time axis. So at time 1, at time 0, I was here. At time 1, I'm here. At time 2, I'm here. Maybe I don't know how to jump. Maybe I jump here, right? So usually you can plot this in time. So there are two things that you can see about a given state. How frequently you see that state. So it happens and happens and happens and happens, right? Or you see how recently you have seen the state. So if I am at the final state, say the one before it is probably important. Oh, this is, sorry, not in this picture, not the right thing. So if one of them is the final state, so whatever shows up before it is important state. Right? So there are two aspects to what is important. In a game of chess, or the last few moves that you made, which I assume most of you have played chess or Go or whatever, the last few moves is when you get the decision, right? Are they the most important ones? Or is the whole process of building up the positions that show up over and over and over, are they more important? Right? So there are two kinds of people. Some say the frequency is important. If your position shows up, if your state shows up in all solutions, then it's probably important. And the other version is the recent. How recently you saw it before the final decision. That is important. Okay, so this has been traditionally been kind of the marker of saying, also for other reasons, but this is the reason why one comes up with what's called, well, I think these language is different from what I had, so I keep forgetting what they call it eligibility trace. Yeah, I don't want to introduce more words, but that's not the word I knew before I saw this in this context. But to implement this kind of a dichotomy, what's more recent and what's more frequent, you keep track of both these things. You keep track of both your frequency and your recency. Right? And this also depends on a parameter. And the parameter is again saying, or do I value frequency more, or do I value how recent something is more? Right? And of course, in different problems, there is different things different processes at work. Yeah, it is difficult to talk. And in some cases, frequency will be the real thing to worry about. In some cases, the recency will be more to worry about. Okay, so you need a parameter lambda. So lambda is a parameter in 0, 1. Right? So for everything, and you're attaching these numbers to a state. So you have attaching a function from states to R. So each of these E's is a function from state to R. And it also depends on two things. So E depends on t, the time, and the parameter lambda. Okay. So what is, well, E lambda t of a state as? It is, okay, maybe I will do a tautological thing because I want to define it like that. E0 lambda of S is 0. Okay, so initially we have nothing. Okay? And you say E lambda T of S is, so you have a gamma factor, you have a lambda factor. So what you had before, till the last time step, you scale it by lambda. So if your lambda is 1, you think it doesn't matter. Time doesn't matter. You will always keep the value of what you had as before. If lambda is 0, you want to forget everything that was before. Right? So lambda in between, it means you're keeping some effort from past and some effort from or ignoring some part. And plus, so now I say this. What does that mean? How many people are familiar with that? The indicator function, right? So this means if you are in state st, if s is your state at time t, then you add 1. So if you see the state at time t, you add 1. If you don't see the state at time t, you don't add 1. So if you look at, I don't know what these things are called. So I have time here. You know how kids keep track of, I don't know if you play any of these games like cricket. So you keep track of scores by adding lines. It's like scoring in, so we use 10 digit, this is unidigit, not binary, unary scores. Right? So whenever you see the state, you keep a line. Right? So when you see the state here, it goes down between here and then goes up. It goes a little bit down, but you see this thing again, so you add 1. Then you don't see it, it goes down. But you see 1, you go up. Oh, sorry, yes. Let me guess this. I didn't see that one. So also don't draw it correctly. Now you go down and you go up. Right? You go down and you go up. So every time you see the state, your function becomes bigger. Otherwise, it just becomes less. And if you see the function, it becomes bigger again. So how this thing slopes, how does this thing slopes, depends on your parameter lambda. It sort of slopes exponentially in lambda. So this is your eligibility trace function. And it's a useful, not just for these kind of algorithms that I'm going to say. It's a useful kind of function to keep keep these two heuristics in mind. Whenever you want to keep the balance between these two things, this is the function you should think of at first. So forget about reinforcement learning. Anywhere where you want to keep balance between frequency and recentness, then you should think about these kind of functions. Okay. So of course, these people are also going to do that here. So is that good? So now the question is, how can we implement, or can we sort of approximately implement our TD lambda algorithm by learning one step at a time, but keeping track of when was the last time. So this function, sorry. So this function keeps track of the last time we had looked, sort of the weight given to the state. It keeps track of how to weigh the state that we are in. And this is exactly good for doing a sort of biased version of TD lambda of this TD lambda algorithms. Any questions? Okay, so remember what we saw before is what's called the forward TD lambda. It requires you to know the whole episode to update. So as such, this required you to know the whole episode to update, because what did it do? It computed G lambda as a weighted sum, lambda to some whatever, n minus 1 Gn. Now each of these Gn's was a sum, which I'm not going to write out. But you needed to know the whole episode to calculate this thing. Otherwise, you cannot calculate this thing. And this is a problem. We don't want that. So there is a cheat algorithm, which is called the backward TD lambda. And these two are not the versions that are simply were first introduced. They are not equal. There is someone who has come up with ingenious ways of making them equal, but I'm not going to talk about that. Not make them equal means there is a version here which becomes equal to that. There is a perfect version. But let's just look at the simple enough version. And for most practical purposes, this is the algorithm that people use. For most practical purposes, this is the algorithm that people use, and this is the algorithm that gives you all the theory. This is the theory, this is real life. Okay? So there is this saying that you should always remember that in theory there is no difference between theory and practice, but in practice there is. Right? So this is the practical algorithm. It's practical because it can be updated in one step. And how do you update is, remember we have this error, the TD error. At time t is the reward that you get from your one observation and the value at the next current value, as you have assumed it to come. Now everything will become E. this is your sort of target, so to speak. This is the target of what you want to get to, right? Whereas what you should do, you should scale this. You should scale this by your memory. Okay. So what you should do is you say, I will scale this by E lambda t. So scale. This is a scale factor. So what you should think of the target equals E lambda t s times. This is what you're looking at. So you have somehow kept the memory of how frequently you have been seeing the state and have added this information on a lambda scale to your algorithm. Okay. Once you understand that, okay, let me just write down that. Then what you do is you update the new value is your old value plus alpha times. Okay, now I'm getting confused, but I would just say a factor of this, E lambda t delta t. But we'll see if my memory is right. It should say something like that. If it doesn't, tell me. Sorry. So this is the practical algorithm. It tries to become the theoretically good algorithm by doing this kind of heuristic cheating. And there is some version of it, there is a version of it where you can prove that it's equivalent. So, oh, we are running almost out of time. So that's okay. So all these algorithms are doing what? They are all trying to evaluate the policy from experience. What reward you get and what state you start at a state, you do an action, what reward you get, what state you get into. So you're learning the value of your policy in all these algorithms by experience. So this is policy evaluation in a model-free setting where you learn directly by experience. Nobody has given you the transition probability. Nobody has given you the reward functions. You're learning by experience. So this is practically the most reasonable plan people use in these kind of settings. Okay. So I think some things are obvious, and I'm not going to, but I have added that information here. So if you add up these TD increments, they are the same thing as what you will get over the whole episode. You get the same number. This is just doing very bare expand this sum and expand that sum on both sides, and you'll get the same number. There is no mathematics involved. It's arithmetic. Okay, but so to come up with this kind of function is more mathematics. This is the logic why one should consider the backward TD lambda algorithms as being almost as good as the forward TD lambda algorithm, with the added advantage that you can actually implement it. Okay, so this is all about policy evaluation in a model-free situation. Next time we will do the control in the model-free situation. Okay, and then we'll spend some time understanding mathematics a little bit more carefully. Okay, before we go So these are the first algorithms that were really efficient, what we are doing now. And then we're going to go to the next generation, the policy estimate, where, remember the first slide. Go back. Here you loop from a policy to the value and back to the policy. But if you are familiar with deep learning, policy is just a function, say, or a probability. Why don't you just try to improve the policy itself by considering as a function? So that is the next level, but we are still not there. We should really learn these set of algorithms because they work. Okay, so that's all for today, and yeah, I'm going to stop this now.